Alright, students, in our last lesson, we learned about rational and irrational numbers and the number system in general. Today, we will cover the final part of this topic about real numbers. If you are new to the channel, please subscribe to join the family. My name is Wandasan Warku. Enjoy. Definition of real numbers. Real numbers are all the numbers that can be represented on a continuous number line. They include every point on an infinite straight line, extending in both directions from zero. Formally, the set of real numbers, denoted by capital R, consists of two disjoint parts. The first part, all rational numbers, which is represented by capital Q. Numbers expressible as P over Q, where P and Q are integers. Q is different from zero. Fractions, integers, terminating or repeating decimals. All irrational numbers. Numbers that cannot be expressed as such fractions or non-terminating, non-repeating decimals, like square root of 2, phi e. Real numbers fill every possible positions on the number line with no gaps. This property is called completeness, unlike rationals or which have holes where irrationals live. The reals have no missing points. This makes them essential for describing continuous quantities in the real world, such as lengths, times, temperature, and distances. The real numbers form the foundation of most mathematics taught in school and beyond, enabling calculus, geometry, physics, and engineering. Properties of real numbers. The real numbers form a complete ordered field, meaning they satisfy these key axioms. Field properties. Arithmetic works smoothly. Closure under addition, subtraction, multiplication, and division, except by zero. Commutative, associative, and distributive laws. Additive identity, 0. Multiplicative identity, 1. Additive inverses or negatives and multiplicative inverses, reciprocals for non-zero numbers. Order properties. Total order for any two reals A and B, exactly one of A is less than B, A is equals to B, or A is greater than B, holds trichotomy. Transitivity. Addition preserves order. Multiplication by positive numbers preserves order. Completeness. Least upper bound property. Every non-empty subset of real numbers that is bounded above has a least upper bound or supremum in the reals. This is what makes the reals complete. No gaps exist. For example, the set of rationals less than square root of 2 has a least upper bound of exactly square root of 2, or which is real but irrational. Density. Both rationals and irrationals are dense in the reals. Between any two real numbers, there are infinitely many rationals and infinitely many irrationals. Archimedean property. For any positive real x, there exists a natural number n such that n is greater than x, no infinitesimal small positives. This property ensures the real numbers can model continuous phenomena perfectly. Representation and types. Real numbers are represented primarily on the number line. Positive reals to the right of 0, negative to the left, 0 at the origin. Subsets include natural numbers 1, 2, 3, continuous infinitely in positive direction. Whole numbers 0, 1, 2, 3, continuous infinitely in positive directions. Integers negative 2, negative 1, 0, 1, 2, which is continuous in both directions. Rational numbers, fractions and their decimals. Irrational numbers, square root of 2, phi, e, or golden ratio, etc. All reals have decimal exponentials, terminating or repeating or rational, or infinite non-repeating or irrational. Operations on real numbers. Operations follow the usual rules and results are always real. Addition or subtraction. 3.14 plus square root of 2, which is equals to 4.554, continues infinitely, which is real number. Multiplication 5 times 2, which is equals to 25, or irrational, hence real. Division square root of 3 divided by square root of 3, which is equals to positive 1, which is rational number. 1 divided by 5 is irrational number. Exponents and roots most yield reals. For example, negative 8 the power of 1 over 3, which is equals to negative 2. The reals are closed under these operations except division by 0. Comparison with rationals and irrational numbers. Rationals are countable, have repeating or terminating decimals, and leave gaps. Irrationals are uncountable, have non-repeating decimals, and fill those gaps. Reals, rationals union with irrationals form a continuum with no holes, are uncountable, and allow limits, continuity, and calculus. Removing the rationals from the reals still leaves a dense set or irrationals, and the line looks the same, illustrating how small rationals are compared to the whole continuum. Here are 5 clear examples showing different aspects of real numbers. Any integer, for example, negative 7. Negative 7 is real number because it is rational number and lies exactly on the number line at the integer mark. The second example, a fraction. For example, 5 divided by 3, which is equals to 1.666, continues infinitely, repeating, which is repeating decimal, rational number, real plotted by dividing the interval between 1 and 2 into thirds. The third example, a square root of 2, which is equals to 1.414213, continues infinitely without repeating, which is irrational number. Real length of diagonal of unit square, constructed geometrically on the number line. The fourth example, phi, which is equals to 3.1415926535, continues infinitely without repeating. Transcendental irrational number. Real circumferences or diameter ratio of any circle appears everywhere in nature and physics. The last example, an integer decimal. For example, e, which is equals to 2.71828, continues infinitely without repeating. Base of natural exponential, irrational number, and transcendental. Models continuous growth or compound interest population. Real numbers provide the complete continuous framework needed to describe the physical world or universe accurately. Without them, many scientific and mathematical concepts like limits, derivatives, integrals, and infinite processes would be impossible.